Now let's look at 411 for corrective action. 411.1 begins with the laboratory shall establish a policy and a procedure and shall designate appropriate authorities for implementing corrective action when non-conforming work or departures from the policy and procedures in the management system or technical operations have been identified. This establishes that labs need a corrective action procedure and a process for how they handle corrective actions. 411.2 says the procedure for corrective action shall start with an investigation to determine the root cause or causes of the problem. 411.2 is important to note as well, as it is the first step in our corrective action process. When creating your procedure, please ensure that you are starting with cause analysis. There are many different ways that a lab can go about performing a corrective action investigation. One way that is used in many industries is the 8 Ds, or the 8 disciplines. The 8 Ds, better known as the 8 disciplines, was developed by Ford to address problems within their products and processes. Nowadays, 8 Ds is utilized by companies around the world in and out of the automotive industry. Step 0, found in the middle, is to plan. Write down the original problem and estimate the resources necessary to solve and correct the issue. 1. Team. Assemble the team and define the team leader. The team should consist of no more than 8 people, but should include the people who impact the process or are impacted by the process in varying levels of personnel. Include the naysayers, the yes men, and everyone in between. They must be familiar with the process, and you must have a facilitator who can keep people on point and manage the team. 2. Problem. Define the problem statement. 3. Correction and containment. If necessary, stop the process to prevent further impact and verify that the containment worked. 4 is corrective action and escape. Perform a cause analysis. If a fishbone has not been created for the process, then a brainstorming session might be necessary, and then assemble the possible causes into a fishbone diagram. Then you can employ tools like the 5 Whys or the force diagram, cause and effect. 5. Corrective action. Based upon the potential causes, risks, and costs, identify and document the corrective action. Determine how you are going to monitor the corrective action and define the objectives that will equip you to determine effectiveness. 6. Implement and validate. Implement the corrective action and through the monitoring techniques, assess if the actions applied were effective. 7. Prevent recurrence. Define what measures you will deploy to prevent recurrence, reduce the monitoring rate, and refresher training, etc. 8. Closure and celebration. People want to know that their efforts made a difference. Case studies are helpful here. Celebrate those who contributed to the success and share the victory with others. Corrective action versus correction. Correction is the previous slide portrayed. Correction does not come out of thin air. It comes from a complaint or not conforming work. Now, while we did not discuss non-conforming work in the section 4.9 of the standard, sometimes stopping the work, fixing or immediately correcting the issue, and evaluating the impact is very important before we arrive at the corrective action phase. This is especially true when it pertains to health and safety. Correction can be made in conjunction with corrective action, but sometimes you must stop the bleeding before you do your cause analysis, otherwise the consequences could become much greater. Corrective action. Sometimes, like in the case of a teething baby, symptoms usually including crying, fever, runny nose, which appear like a cold, the doctor can only address the symptoms when it clearly understands the cause of the problem. The right response in situations like this is to prescribe something to mitigate the symptoms, such as children's Tylenol. Corrective action is to take to eliminate the cause of a nonconformity and to prevent its recurrence, and address those symptoms. An example of a corrective action based off of a complaint. The complaint itself being, my data doesn't match what I expected the result to be. Your first step is going to be to correct and evaluate. You might have you immediately check the raw data to make sure something wasn't transposed. This is easy enough to correct with a revised report if that's the case. If that wasn't the case, you would need to evaluate and likely check to be sure the quality control passed for that particular batch of samples. If not, why was the data reported when the quality control didn't pass? Should the samples have been flagged and they weren't? Should the samples have been reran and they weren't? What if the quality control passed? Then maybe you should check to see if any of the other samples in that batch had an unexpected result in which you might consider that the samples may have been switched. If you still have the sample, maybe you rerun the sample to see what the result is when you rerun it, even if it's outside of hold time. Cause and corrective action. Once you've determined what likely happened, you'll need to correct it and likely figure out a way to avoid it in the future. If we go with the easiest option of transposing numbers into the report above, we correct it by issuing a revised report. But we still need to consider why this may have happened. Was it a simple human error that just needs additional review before things go out? Was the laboratory understaffed and so the individual putting their numbers into the report was rushing? Do we need to consider moving the task around or bringing in additional help for the task? We want to monitor. Once you've determined what the cause of the problem was and put in plan and action, we need to monitor to make sure that whatever you implemented actually takes care of the problem. Maybe this happens weekly or monthly when reporting happens to make sure that the corrective action worked. And then review. Further out, you need to review the corrective action as part of your management review process, and once again make sure that what you did fixed the problem. There are multiple ways to do corrective actions. One of the more common ways is the 5 whys method. You can set up a chart similar to this that you see on the screen and record the questions as you move to the cause of the problem. The problem being, in this specific path, the nonconformance being investigated. To be more effective in your cause analysis, the 3-legged 5 whys is used. Escape, use this path to determine why this problem was not detected before. Why did the nonconformance reach the customer? And systematic, we use this path to determine when this nonconformance is repeatable. When asking the why, the answer should be able to return to the previous cause or effect. For example, the problem being the car would not start this morning. Why? The car made a clicking sound when I turned my key. Why? The car battery appears to be dead. Why? The headlights were left on last night and killed the battery. Therefore, the car would not start. The 5 whys can help get to the root of the problem and is a cheap and effective tool to utilize in your laboratory. When do you turn off those 5 whys? Well, it may not be 5 times. We need to make sure that the cause has been addressed and we can prevent recurrence. The fishbone is another common method for performing cause analysis, but is often coupled and preceded by using the brainstorming method. Whichever method or technique used is not of critical importance as it is to find the actual cause of the problem. Rarely is there a root cause. For all intents, the root cause of any nonconformance is people. They created the materials, the machines, the methods, the measurements, and control the environment. But a good cause analysis doesn't lay fault on the people, but rather the process. Typically, a nonconformance is a series of causes that reveal the effect. Let's consider the Space Shuttle Challenger disaster of January 28th in 1986. A seal in the shuttle's right solid fuel rocket booster designed to prevent leaks from the fuel tank during liftoff weakened in the frigid temperatures and failed, and hot gas began pouring through the leak. The fuel tank itself collapsed and tore apart, and the resulting flood of liquid oxygen and hydrogen created the huge fireball believed by many to be an explosion. Looking at the data set of information, there are 2 databases. Both use the same set of 5 attributes. 1, the primary O-ring erosion and/or blow-by. 2, primary O-ring erosion only. The 2 databases are identical, except the second attribute of the first instance. The motivation for collecting this database was the explosion of the USA Space Shuttle Challenger on January 28th of 1986. An investigation ensued to the reliability of the shuttle's propulsion system. The explosion was eventually traced to the failure of one of the 3 field joints on one of the 2 solid rocket boosters. Each of these 6 field joints, including 2 O-rings designed as primary and secondary, which fail when phenomena called erosion and blow-by both occur. The night before the launch, a decision had to be made regarding launch safety. The discussion among engineers and managers leading to this decision included concern that the probability of failure of the O-rings depended on the temperature at launch, which was forecasted to be 31 degrees Fahrenheit. There are strong engineering reasons based on the composition of O-rings to support the judgment that failure probability may arise monodically as temperature drops. One other variable, the pressures at which safety testing for field joint leaks was performed, was available, but its relevance to the failure process was unclear. Draper's paper includes a menacing figure graphing the number of field joints experiencing stress versus liftoff temperature for the 23 shuttle flights previous to the Challenger disaster. No previous liftoff temperature was under 53 degrees Fahrenheit. Although tremendous extrapolation must be done from the given data to assess risk at 31 degrees Fahrenheit, it is obvious even to the layman to foresee the unacceptable high risk created by launching at 31 degrees Fahrenheit. For more information, see Draper's 1993 paper or the other previous analysis. The task is to predict the number of O-rings that will experience thermal distress for a given flight when the launch temperature is below freezing. The cause information is the number of O-rings at risk on a given flight, the number experiencing thermal distress, the launch temperature in degrees Fahrenheit, the leak check pressure, or PSI, and the temporal order of flight. The goal is to determine the best way to fix the problem, not just put a Band-Aid on it so that the actions applied prevent recurrence. 4.11.3. When corrective action is needed, it must be performed. The corrective action completed must appropriately fit the severity of the problem. The corrective action process must be documented. Make sure you're keeping records of your corrective actions and make sure your corrective actions are not too big or too small for the problem. If you fail a PT, you need to implement corrective action, but that does not mean that the action should be to fire the employee who failed. 4.11.4 states you must monitor corrective actions. Put a placeholder at the bottom of the corrective action form for monitoring signatures and notes. It's an example of ways you could go about that. Always revisit corrective actions during internal audits and management reviews. 4.11.5 is to audit. You must do an internal audit of affected areas if it appears the issues extend beyond the current data. This is an audit of the entire lab, but specifically of the area where the problem is located. This would be if the problem is systematic or if it casts doubt on other lab data or lab work. This does not have to be, again, the full audit of the laboratory. 4.11.6 requires that you have a documented procedure to address the previous sections, addressing corrective actions, including selection and implementation of actions, monitoring of corrective actions, and additional audits if needed. We must also identify in this procedures who is responsible for assessing each QC data type, ultimately finding the issues, and initiating or recommending corrective actions. Systematic errors, also called systematic bias, is consistent repeatable error associated with faulty equipment or a flawed experimental design. These errors are usually caused by measuring instruments that are incorrectly calibrated or used incorrectly. However, they can creep into your experiment from many sources, including a mishandled or aged instrument. For example, plastic tape measures become slightly stretched over the years, resulting in measurements that are slightly too high. An incorrectly calibrated or tailored instrument, like a scale that doesn't read 0 when there's nothing on it. A person consistently takes an incorrect measurement. For example, they might think the 3/4 mark on a ruler is the 2/3 mark. Systematic errors produce consistent errors, either a fixed amount like 1 pound or proportion like 105% of the true value. If you repeat the experiment, you'll get the same error. Systematic errors are consistent in the same direction, that is, they're always 50 grams, 1%, or 99 millimeters too large or too small. Take a moment to read the compliant example. The corrective action procedures need to address all of the requirements of the standard. They should describe who will initiate the procedures and follow up on them, how they will be documented, and when cause analysis is needed. In looking at this non-compliant example, you might note that it does not include such things as cause analysis and that additional audits would be required or monitoring of those corrective actions. Some of the most common non-conformances within corrective actions are noted here. We don't see many findings with the actual corrective action procedure, but rather with labs not implementing corrective actions when they need to. Remember, when something like a repeated QC failure occurs, your lab needs to be open to a corrective action investigation. Likewise, in the first example, if your refrigerator or incubator is found outside of acceptable ranges, you need to be opening a corrective action to ensure that the data was not affected and find out what caused the change in temperature.